myself, which is always my least favorite part. Um, so like I said, today we are talking about piecewise functions. Piecewise functions. Piecewise functions are like not functions. Um, it's going to be a little weird because I actually have to like kind of draw graphs, but we'll go over this and I'm going to show you how to do them, and then I'm going to open up Delta Math and kind of show you how to graph them in Delta Math, and then I'll let you go. But I have to change colors because I can't just, it's too early in the morning for me to look at all that black. So piecewise function, what is it? It is basically a function that's got two or more functions in it, right? It's if you remember, like before we left, we were doing like systems of equations where we had like um, different like sets of equations that had common solutions, and we had to figure out how to work them together. When we talk about piecewise functions, it's basically a makeup of two or more functions, and they each have different domains. Like they're two or more, I can't. Man, I am not ready to be back at work. Can you tell? A makeup of two or more functions. And giving you the definition is not a really good way to explain it. It's so much better to explain it by seeing it. And so we're going to start by evaluating them so that you can kind of see how they work, and then we'll move on. So when we are evaluating, anytime we say evaluating in math, it means we're giving you a value to plug into something. And that's always going to be kind of like how we deal with evaluating. Haiti, you need to be on camera, please. Aiden, you as well. When we are evaluating functions, if I have a piecewise function that's like given f of x, which is the name of our function, equals, and what we're going to do is we're going to have multiple equations in here. We can have 2 or 3 or 4. I will never make you do more than 3. But we're going to have, so say I have like x squared minus 1 if x is less than negative 2. And then I'm going to have 5x plus 3 if x is greater than or equal to negative 2, right? What that means is we're going to look at the parameters on each piece. It says if we're plugging in, this one says if we're plugging in an x value that's less than negative 2, we're going to use this equation to find the value. If we're plugging in an x value that's greater than or equal to negative 2, we're going to use this equation to find the value. That's all piecewise means. We're going to look at the parameters that we set out. So it says if x is less than negative 2, we're going to use x squared minus 1. If x is greater than or equal to negative 2, we're going to use 5x plus 3. And so when we're evaluating a function, I'm trying to move my screen without writing on it. So when we're evaluating a function, it means they're going to give us the value that we need. So say I want to know at f of negative 5. So at f of negative 5, well, negative 5 is less than negative 2. So I am going to use the x squared minus 1 value. So it's going to be negative 5 squared minus 1, which equals 25 minus 1, which is 24. So not too difficult as long as you know what to plug in, right? If I get f of negative 2, we are going to use the one that says x greater than or equal to negative 2, right? Because negative 2 is definitely equal to negative 2. And so I would plug it into, dang man, I can't stop accidentally writing on this screen. I'm having a day. Having a day. All right. So now I'm going to use the 5x plus 3, and anywhere there's an x, I'm just going to plug in negative 2. So 5 times negative 2 plus 3 is going to give me negative 10 plus 3, which is negative 7. And so it kind of gives you an idea of how all of that works, right? All you're going to do is look at, when you're evaluating, you're just going to look at, well, what are we plugging in, right, to determine how we're going to find the value of it. Let's look at one more example and then we'll move on to graphing, because actually we don't even have to do that because I gotta get back in the swing of things here. I'm like way off right now. Like you'd have thought I just took the whole summer off and not just the weekend. All right. So say I have a new function and it's saying that we're given f of x equals 1/2 x. Ooh, a fraction. They're giving us a fraction. Plus 3 if x is less than or equal to negative 4. And then we've got minus x minus 1 if, this one's interesting. Negative 4 is less than x is less than 1. We'll talk about that in just a second. And then we've got 2x cubed plus 9 if x is greater than or equal to 1. On your delta math assignment, I stayed away from higher powered functions. I tried to keep it all linear for you, so I didn't take it into the higher levels. But let's look at this middle part. Like if we look at the first part, it goes x is less than or equal to negative 4. So anytime we put in an x of negative 4 or less, we're going to use this first equation. But this one shows negative 4 and 1, right? Notice there's no equal to sign on either of those. So if the numbers fall between negative 4 and 1, you're going to use that equation, right? But if they're equal to negative 4, like if it's equal to negative 4, you got to use the top equation. And if it's equal to negative 1 to 1, you're going to want to use the bottom equation. So you're looking at like negative 3, negative 2, negative 1, right? 1/2, anything that falls between those, you're going to use that middle equation, minus x minus 1. Anything big 1 or larger, you're going to use the bottom equation. And that's really all there is to it in terms of evaluating. So if I said I want to find f of, let's not even make it, but f of 2. I'm having a f of 2, right? If we want to know what that equals, well, we go, okay, well, f of 2, that's bigger than 1, right? X is greater than or equal to 1. So it's going to fall in that third equation. And so we're going to have 2x cubed plus 9. And just wherever the x is, we are going to plug in 2. So we'd have 2 times 2 cubed plus 9, which is going to give me 2 times 8 plus 9, which is 16 plus 9, which equals 25, right? So not too difficult, because once you know what equation to use, all the equations themselves are fairly simple. What if I have f of negative 1? F of negative 1 is between negative 4 and 1. And so we would just use this middle equation. So we'd use minus x minus 1. Remember, if I'm plugging something in, always put it in parentheses. And the reason for that is we have a negative in front of this x. You want to realize that it is a negative 1. So here we would have negative 1 minus 1, which is the same as saying 1 minus 1, which is just 0. Kind of follow? Does that all track for you guys? Everybody kind of on that one? Because I want to get into the graphing portion, because that's always so time consuming. I'm going to take your silence as pure understanding. It's probably a mistake on my part, but I'm going to do it anyways, because why the heck not? So if we're going to graph one of these, we still have those parameters, right? Like we're still looking in terms of, we've got these sections that we have to figure out, right? So if I have, say, f of x equals, it's my favorite part, drawing the little thing, x if x is less than or equal to negative 3 and negative 2x plus 1 if x is greater than negative 3. So we have some things happening here, right? The first thing we have to talk about is we have to talk about what are the domain and range of these functions. And the domain, does anyone remember what a domain is from when we talked about functions? You're killing me, people. You're killing me. It's like teaching a podcast. The domain is any possible thing that x can be, right? So we look at this, and this just says x is less than or equal to negative 3. So if we look at the domain of these functions together, we kind of cover the gamut, right? Because this says that x can equal less than or equal to negative 3. So negative 3 and forever in the negative direction. This one says x is greater than negative 3. So it's starts at negative 3 and gives you everything in that positive direction. So you've pretty much covered all real numbers. So you could say that the domain, when they're together, goes from negative infinity all the way to infinity, right? It's never going to get, there's no real number that you can't plug into it. The range, if the domain is all the possible inputs of x that you can put in, the range is all of the possible outputs of y that you're going to get. So they're saying whatever I plug in, what's going to happen. And And in this case, we'll look at it after we graph it and try and figure out what the range is. And I got smart on this one, and I got me a graph to insert because I didn't want to draw one. So here I have this graph, right? And if I want to look at this problem and graph it, it's saying that if x is less than or equal to -3, that f of x just equals whatever x is. What that means is if x is -3, that means its y is also -3, right? If x is -4, the y is -4. If it's -5, it's -5. So if we did this, this would go on forever in that negative direction. Does that make some sense in terms of the graph? I gave it a solid dot because x can equal -3 in this case. If x is not equal to -3, if it's greater than -3, we're going to look at what happens to the graph. So here I have 2x plus 1. If I plug in -3 there, so if I have -2 times -3 plus 1, I'm going to get, what is that? 6 plus 1, which is 7, right? So at -3, I would have 7, and it would be an open dot. Does anyone remember why it would be an open dot and not a closed dot? No, no, you don't. It's an open dot because it does not actually equal -3. It starts there but doesn't equal it for this equation. If I'm plugging in, say, -2, right? I can keep putting x's in, right? -2 plus 1 is 4 plus 1, which is 5. So at -2, we've got a point at 5. And we could do this for all of these, and we can kind of figure out what the slope is on this problem when we kind of graph them like this. And it's going to go something like that. I'm not doing the proper graph. I don't feel like putting in like 8 different values for this, but you can kind of get an idea of what's going on in terms of the graph from -3 on. We're going in this downward negative direction, right? From -3, not counting, but towards the positive direction, higher up, we're still decreasing, right? This one is going down, but into that positive side direction. And you should be able to find, like in a proper graph, when you do it in Delta Math, you should be able to find the tendency for each of these. And if you look at this in terms of the range, all the possible y values, it's not going to be all real numbers because based on this and the tendency, this one is going down in this direction and this one is going down in this direction. And you'll notice that it never goes over 7. Nothing's going to make it go higher than 7. And so in that case, our range would be our range would be sorry, y is greater than, sorry, that's not greater than, it's less than. Y is less than 7, right? Never actually equals 7 because we have an open dot there. We just know that y is less than 7. It can be anything less than 7, but it can never be above 7 or equal to 7 because everything goes down on the graph from there. I'm not going to show you more examples on paper because I would rather show you an example or two in Delta Math because that's where you're going to be doing your assignment just so that you can see how to graph them. And then I will let you go. So let me open up Delta Math. And we are doing, I should have opened this before class, but the evaluating piecewise functions, you'll see is just simple. You're just going to plug in 2. You're going to pick which one, right? It says this one's f of 2. And so you have to go, well, which one do I use for 2? Well, x equals 2. You would use, it's just, y, your answer would just be -3, right? You don't even have to do any work on a problem like that, right? Because you know where when it equals 2, your solution is just going to be -3. There's no equation to put in it, right? Let's look at a new problem so that we can see one that maybe we do have to work on. This one says at x equals, boy, these are all really easy. It's just giving you the actual -5. Let's see one where we actually have to find it. All right, this one says find 2. This one feels a little bit like an error to me. -1. This is greater than -1. This is equal to -1. They're actually all that easy because I just gave you the level 1s in your evaluate. So that should be pretty easy. In the graphing, I gave you level 1 and level 2. I did not go into level 3 because it got out of the linear. But we'll look at level 1 just so you can see because it's all just graphing. And it says graph the following function on the axes provided. And our first equation says -3x minus 6 for x less than -1, which means it's going to start at -1, right, with an open dot because it doesn't equal -1. And so we would plug -1 into this function, right? And -1, that would make -3 times -1 is +4 minus 6, so it would be -2. We could do that on paper, but I'm just doing it in my head because I'm more interested in showing you how to graph them. So at -1, I have a point at -4, and it'll be an open point. At least it should be if I could actually, oh, that's why, because I got this up. Click and drag to make a line, click the line to delete it. Okay, I got to start. The slope on this is -3, so it's going to go down 1, 2, 3, and over 1. That's how you have to do it. Okay, I was trying to figure that out. And then I just click on it to open the dot. If I double click on it, I get an arrow showing that it's going that way forever. The other part says if it's greater than 5, we're going to use this one, right? So at 5, we've got, well, -2 times 5 is -10 plus 8 is -2, right? So at 5, I have a point at 5, -2. And then if you look at that slope, that's a -2. That slope is determined by what's in front of the x, which means we would go down 2 over 1. This one would also have an open dot. This one, we just click on it again and we get the arrow. And so this is how we determine it, right? Everything from this equation is going to follow this pattern, right? Every point that comes after it's going to have the same slope. it's not asking you about domain and range. So, oh, look, I screwed up. I screwed up because when I plugged in the negative, that was supposed to make the positive. This is my bad. This should have started at +4 and gone up. That was just me screwing up because I did the math in my head. So let's look at another one. This one's saying that if x equals -1, we're going to plug -1 in there, and that's going to give me +5 minus 11. +5 minus 11 is -6. So at -1, -6, we have a point, and then we have a slope of -5. 1, 2, 3, 4. Let's go up 5. 1, 2, 3, 4, 5, and then we'll go over -1. Because remember with slopes, you can go in either direction. We're going to open that dot. We're going to arrow this one, and we are good. There's an issue with this one though, right? I don't want to put this one in yet because what are we saying about this one? We're saying that x is less than -1. So it's going to go in this direction, not this one, right? Because nothing for this equation is going to have an x value of greater than -1, right? Everything's going to be going in that negative direction because we're saying x is less than -1. So we have to do test points that are less than -1, right? So -2 would have been our test point on this one. And then like -3, if we had -3, it would take us up to 4. If we had -5, it would take us. So what happens when x is greater than 4? Anytime x is greater than 4, the solution is -1 all the way across. Open dot, arrow, right? It says x is greater than 4, right? So at 4, every time x is greater than 4, we get an outcome of -1. And this should be how our graph plays out. Does that make some sense? The cool thing is with Delta Math, you can play with it a little. If you're not getting it, you can watch the video on it. Nobody's really talking to me, so I'm going to assume you're getting it. I'm probably assuming wrong, but that's all you guys are giving me. So we'll call that we'll call it done. We'll call ourselves done on this one. I'm going to stop the recording.